Hi, everyone. Emmanuelle, is that the URL for the?
No, that was for the boxes.
Oh, could you write down whatever you? There's actually, you can find it here if you go to github.com. No, that's not right, because this is my clone of the repository. So wait for Emmanuelle to get the tutorial URL. OK, so essentially, we're going to start from the basics of image analysis in Python. And if you're familiar with a little bit of NumPy, then that's all you need to follow. So hopefully you've got these packages. If you have Anaconda installed, which I would recommend, then you've got everything you need. So Python, NumPy, SciPy, matplotlib, and Scikit image, of course. OK, so also, if you have any installation issues or whatever, raise your hand, and Emmanuelle can go. And during Emmanuelle's section, I can go and help you out. All right, so we'll start with the first section, which is that images in the SciPy and Scikit image world are just NumPy arrays. So as I said, if you know a bit about NumPy arrays, then you can do image processing in Python. All right. So let's just have first of all, if you're not familiar with the IPython notebook, this is something that you want to do almost at the start of almost every notebook. This first line is for making your Python. Is that a little r?
It's a little r.
Lowercase r.
And what's the first one? Is that a Z or a?
Yes. All right. OK, so that's where you download all of these notebooks.
I also posted the link on Twitter if you guys want.
Google says it's been disabled because it violates their terms of service. What's I going to do?
All right. Sorry, I'll keep going while people get their installation sorted. And I'll just try to move slowly so people can catch up. So as I was saying, these two statements just let you write Python 3 code that will also work in Python 2. And public service announcement, you should probably be moving on to Python 3 by now. And this will basically let you display plots and images embedded in the notebook instead of having a pop-out window. OK?
Does the link work for some people?
It might be because you created it or you have it cached or something. OK, so first things you need is to import NumPy and import these two packages from matplotlib. PLT is the pyplot module, which you use to plot basically everything. And CM is the color map. And I'll talk a little bit about what color maps are in a second. So as I said, images are just NumPy arrays. So if we make a random matrix in NumPy using this function, numpy.random.random, so this will give you a 500 by 500 NumPy array with values between 0 and 1. And then if we use the plt.imshow function in matplotlib, you'll be able to see those values. OK? So here's a random image. And that looks random. Color maps are something that we'll talk about a bit later, but here's what you need to know. The default right now in matplotlib is jet, and we'll talk about why that's bad. For images, you probably want to use gray, which basically maps values between 0 and 1 to luminance in black and white. And interpolation equals nearest. What that's doing is removing interpolation between pixels so that you can see the pixels as little squares, and you can see exactly the values of each pixel in your image. So in this cell here, we're just going to look at some example data that is built into Scikit image. In this case, a coins image. And we'll see that, again, this is just a NumPy array. So if I print the type of coins, the D type of coins from the NumPy array and the shape, you see that it's a NumPy array. It's got uint8 values, so integers between 0 and 255. And it has a shape of 303 rows by 384 columns.
Here's a new link.
And that's what it looks like.
It works for some people.
So by the way, once you download that, in order to run the notebook, just run the IPython notebook from the root directory that you download, and then click on 2015 EuroSciPy and click on index.
And if you have an error message telling you that you don't have a recent enough version of the notebook, there is another index, v3, and then it should do the trick for you.
Yep.
If you have trouble, just raise your hand and I'll come and see you.
Okay. So the next thing is color images. So color values in computers are encoded by red, green, and blue values. And so that gives you an extra dimension to your NumPy ND array. So again, we're going to use an example image that comes with Scikit image, Chelsea. I think is it Stefan's cat?
Maybe,
I think so. And again, it's got a shape, and it's got certain values, so have a look. And because it's a color image, you don't actually need a color map. You just render it in its actual color. So here you see it's got 300 rows, 451 columns, and 3 channels.
Does that just assume it's in RGB order?
Yes, that always is assumed in Scikit image.
Yep.
Yeah.
So if you had a three-band image that wasn't necessarily RGB, it would render it as
RGB, that's right. Yeah. There's a color conv module which will let you convert from various other things to RGB. Okay, so as I was saying, these are just NumPy arrays, and this has nice properties, such as drawing on an image is really simple just by using indexing. So if we want to make a red square on this image, we just say from 10 to 110, 10 to 110, draw red. So this is 255 for red, 0 for blue, green, 0 for blue. And there you go. So you've got a red square on the top left corner. Okay. This is just an aside here. You can also add transparency called alpha. If you add, fourth dimension is not the right term. If you add an extra plane on the last dimension. So a short aside that you'll need to know for later. There's a lot of gotchas with these. There's different data types for images that are used. Very common is 0 to 255. That's what a lot of image processing and image formats libraries use. And so 0 is black, 255 is white, and it's encoded as a uint8 integer. But when you're going to be doing a lot of numerical computation, it's useful to have float values so you don't run into things like rounding errors and overflow and underflow. And so there's float images in Scikit image, and there we assume that the range is 0 to 1. Okay, so 1 is white and 0 is black.
What happens if you have a float image where you've got...
It goes outside the range.
Yeah, floats of like 10.7 or something.
So a lot of functions will just work, but functions where it's important to know the range, things like displaying the image and so on, will
look weird.
They might even throw an error.
Okay.
But it's usually an informative error. Yep. Sorry, I forgot to repeat the question. The question was if you have a float value outside of the specified range, what happens? Okay, so again, we're going to look at this. So there's 2 valid images that we can create, and they're essentially the same. Okay, so linspace will give you equally spaced values between the first 2 values. So I get 2500, and then we reshape it as a 50 by 50 image. and we can do the same thing between 0 and 255 and cast it as uint8. Okay, and we can have a look at those, and you can see that they're essentially equivalent. There's one small difference, which is, yeah, that one's in float, and so it can represent a greater number of values, much greater, obviously. For displaying, that makes no difference, because you can only really have 255 values in your monitor. Okay, so to convert between them when you're working with images in NumPy Scikit image, we provide these two functions, image as float, which will convert an image of any type. And there's more than the two that I just said. There's also 16-bit images. And image as ubyte, which will do the opposite. It will convert to 0 to 255. So again, here you can see that you get equivalent images by doing that. So if you, oh, yeah?
What is the size and memory difference if you go from one to the other?
But what do you mean by size?
Well, so
just the memory?
Yeah, just the memory.
Sorry, so the memory floats will typically be 64-bit floats on most machines these days, so it'll be 8-fold greater. Yeah, so sometimes that makes a difference. Yeah. Okay. Yes?
Does it handle sparse data? Do you have a sparse matrix?
It does not.
Okay.
Yep.
Still has problems with the network, or I also have the materials on the stick.
I will say that since it's kind of compatible with NumPy and SciPy, you probably have to do some things in dense format and then go straight back to sparse from whatever you have. Okay, so as I mentioned, we're going to talk about color maps. So let's look at another built-in image, which is a famous computer vision type image called camera. And again, it's built into Scikit image, into the data module. So we load it. We've already imported this, but let's try again. And so, as I mentioned, until the next release, where this is finally changing, the default color map in Matplotlib is jet, and you should not use it, basically, and we're going to see why. So this is what the image looks like converted to jet, and if you've read any kind of scientific paper, you've probably seen jet a million times, because it was the default in MATLAB, and so it became the default in Matplotlib. So lots of people use it. And it distorts the data in a lot of ways. And looking at the face, you can see this. So it looks completely unnatural, obviously. And you can see that there's nothing really going on in the guy's lip, but here it looks like he's got a beauty mark or whatever. So if even for something as familiar as a face, it looks weird, imagine what it's doing to your data. You're actually seeing all kinds of features there that don't exist. So as of Matplotlib 1.5, which is as yet unreleased, you can have the Viridis color map, and I highly recommend that you go to this page, bids.github.io/colormap, where you can see, first of all, the SciPy talk by Nathan and Stefan, who did all the work to create these new color maps, and some basic info about color maps, why jet is bad and why these other color maps are much better. So just be aware of this. Currently, you have to download the current master of Matplotlib and so on to get them, but it'll be out there soon. And just don't use jet, even if you're going to publish a paper soon before Matplotlib comes out, use Grayscale or whatever. Okay, and again, another example. So you can see all of these rings on the left image, whereas it's just a smooth gradient out from the center. So that's not really what you want to do to your data. You want it to look like what it is. And so for the next tutorial notebook, we can actually use the plt.rc params dictionary to permanently set the color map to gray for as long as the session lives. So I would recommend that you do this and do it often. And again, in order to be able to look at your data without interpolation, just set the interpolation to default these as well. So this is how you do the color map gray, but because we've actually set the parameters to these defaults, you can get rid of this, and it should give you the exact same result. Yeah. All right. So that's how you set your matplotlib parameters to something sane. Okay. I did not write this bit, so I'm actually going to be surprised when it works. But the idea is to look at color maps and interpolation and see how they interact. Okay, so you can, this is what your data looks like with these different color maps. And here are all the matplotlib color maps that you can check out. So again, a lot of decent color maps. There's no need to use Jet. So we're not going to dwell on this, but you can play with them in your own time and see which one works best for you. Any questions? All right. So again, in the tutorial, we'll mostly use images that are either bundled with the notebook or in Scikit image. But Scikit image does have an I/O module, which mostly wraps other libraries. And it's gotten a lot better in the past couple of releases. And so you can now do things like read images, and you can actually put a web URL in here, and it's going to work. So let's go back here, for example. I hope this works. I haven't tested it. So if I... Sorry? You're right. I think the link goes to the image anyway, yeah. Yeah. Thanks, though. I know that fails quite a bit. Hopefully that's going to work. Yeah. OK, so that's really nice to be able to just io.imread a URL and start working with an image. And there's also, if you're going to work with a lot of images, which is probably the reason why you're using Python to do image analysis, you can pass a glob expression to imread collection, and it will just call imread on each of those images. And by default, it doesn't load them all at once. It loads them each as you access them. So it's not going to use up a lot of your memory. It's a really nice way to iterate over a collection of images. Okay, so right now all it has is all these links to these files, and if I went to see, yeah, if I iterate over them, then the image is going to come out. So in this loop, only one image is getting loaded at a time. Any questions? All right. So here's the 2 exercises for this section, and we're just going to give you about 5 minutes to do them. So the first one, just like I drew a square, I want you to do indexing and draw an H on a particular image. And the second one, basically get some values and plot them across a row of an image. So it's just to drive home that these are numpy arrays, and you can do all the nice things that you can do with numpy arrays. Yep. So raise your hand if you have questions or need help. Does everyone have the notebooks or not have the notebook? You can also basically do this on an interactive IPython session anyway. Yeah. Do you need help in person? Or?
Yes.
Yeah.
So basically, we are reading these TIFF files.
All right.
And in Scikit image is getting really really weird. So if you can see right here, we're reading the TIFF images, split it, and then the image file, and then basically shape has been totally messed up.
Really?
So, for example, you can see the RGB, it's for TIFF file. The RGB is actually coming from the first channel.
Right.
And then we have to rotate them in numpy. What's the reason for that?
The reason is that TIFFs are often stored in that order.
So the color channel first.
Yeah. However, what version of Scikit image are you running?
I think this is the latest.
Can you just print the version?
Yeah, sure, of course.
Oh yeah, it's right there. Scikit image 0.0. Yeah, that should work.
It was not like that before when I was using 0.10.
0.10.
And then when I was using 0.11, it starts acting in this way.
Okay. Let's talk after the tutorial.
Yeah.
But yeah, that might be a bug, and if that's the case, we'll fix it.
Okay. Is Tony still working on this one?
Sorry?
Is Tony still working on this one?
Is what you?
Tony Yu?
Oh yes. I think very part-time.
Oh, okay.
Steven Sylvester is the guy who's done a lot of work on I/O and really improved it. This is getting messy.
So yeah, so that's fine. So just play around with it.
Y plus 3.
Oh, you check.
Okay, so 3 is the width, so I could put width.
Yeah. But at the moment, yeah.
And I can change that.
Change the width now to 30% because it makes it appear to me.
And I don't think that, because that turns red. That, which turns green.
I'll exclude that cell then. And then let me hit that.
Damn it.
Yes, it's
What?
changes no, you didn't add, you didn't properly mutate out.
What did I do wrong?
You haven't done anything.
Help me.
You've done it to image.
Why is images float given? It says int is not subscriptable.
So that's exactly what that's the square. Now you can go
Oh, yeah, sorry. Nicely done. Yes. All right. So this is fairly tedious but simple. So you kind of want to name your variables nicely so that you don't have to keep typing them as I started doing it. So you start out with a certain row and column, and then you just want to go from row to row height to column plus 3, and that defines a rectangle that's your first arm of the H, and set that to the color. Then you go to the midpoint, and then you give a height of +3, and then you span the strut the whole width. So again, that's another rectangle for the strut, and then you do the right arm. Yeah, so that's the way to do that one. And again, the point is it's easy to manipulate arrays. And this one, if I remember correctly, you just need to subscript the right values. So row 0, that's red, green, blue. And so if you run this on the cat image, you've got your profiles. So at row 50, if you were to draw a line over here, these are the red, green, and blue values that you'd encounter. Okay? All right, so we're going to move on to the next stage, which is image filtering. Any questions on all this? No. All right, so go back to the index and then click on image filters. Is that big enough for the back? Gael? All right, so the preamble as usual, so you want to make it Python 2 compatible, display figures inline, and then set the matplotlib parameters as we discussed. All right, so image filtering is one of the most essential things in image processing. And we're going to start with one-dimensional signals. So again, because NumPy is n-dimensional, it's very easy to do something in 1D and then extend it to 2D and so on. So we create a step signal, which is completely artificial. That's just what it looks like. And suppose you want to find out when this signal changes rather than the signal itself. You might go through each step of the signal and then see if the particular position is different from the next position, and then if it is, then you append it to your list of changes, and then you print those, okay? So now you know that at position 32 and 66, there are changes in the signal. So this works, but it's fairly cumbersome, and it doesn't really extend to more dimensions, for example. So another way is to use NumPy indexing and arithmetic. And so this gives me the whole signal up to the next to last value. Then you subtract from it the signal shifted to the right one, and then the changes are just your non-zero values in this array. All right. So that should give me the same values, and it does. So the last one is this difference filter. And this is where image filtering becomes really powerful. So essentially what you do with filtering and convolutions is you define something that's called a kernel or a footprint or various other things. No one seems to agree on the terminology. And then at every position in the array, you multiply that so you place your footprint, which is multiple pixels wide, or positions in a 1D thing. And then you multiply the values, you take the dot product, multiply the values, and sum them together. So if your filter is 1 minus 1, then you're doing exactly what we were doing before. You're putting the 1 minus 1, multiplying them to the values that they cover, and then summing them together, so you're adding 1 and subtracting the other. And that's exactly what we were doing over here. Okay, so from SciPy, you import the ND image module, which is kind of the root of Scikit image. And then use this convolve to mix your kernel, which is 1 minus 1, with your step signal. And so this is the output. You see that at this point it changes up, and then at this point it changes down. And if you take the non-zero, again, you've got 3266. All right? So the nice thing about this approach is that it generalizes to a whole bunch of things that you can do to signals. So in this case, we're going to make a noisy signal by just adding random noise to it. And that's what it looks like. And so now if you wanted, one way to get rid of noise is to just average. So you take each pixel and you take the average of that pixel with its neighbors and replace it by that value. So by taking an average, you remove noise. So the manual way of doing this is kind of annoying. You just do noisy signal, you take it up to the second last, then you take the middle, and then you take the last one and you divide by 3. That's how you get the average of all the pixels. And so that's a bit smoother than this, as you can see. So that works, but it's kind of cumbersome. With the convolution, you can do it just by defining this array of 1/3 at each position and then doing the convolution operation. And again, you get the exact same result. So hopefully you can see that that's a lot more elegant and extensible. So as the exercise, you want to do a wider footprint. Instead of averaging 3 values together, average, say, 5. So I'll give you just a couple of minutes to think about that, because then we got to rush along. Okay, so here's my solution. You just have to write a wider kernel of length 5 instead of length 3 and divided by 5 instead of 3 and convolve it. Now imagine if we'd wanted to do this the naive way of just taking the signal and doing array operations on it. You would have had to increase this by 2 lines. And it would just be cumbersome and error prone to write. So again, you can modify and experiment a lot quicker by using kernels. So hopefully this works. Yeah, and so you can see it's smoother than before. All right, so let's extend this to 2 dimensions now. So if we make a square, so it's this 3 by 3 square in this bigger space, and you can just do IMShow to look at it. We can do, again, a mean filter, but this time in 2 dimensions. And as I mentioned, it's a lot easier to extend. So doing this kind of array arithmetic in 2 dimensions will get hairy really quickly. Whereas to do the mean filtering using convolutions, we just need to define a 2-dimensional kernel divided by the right amount, and then convolve the image with this. So here's a way to see what that's doing. So this was written by Tony Yu. It's a pretty cool demo. On the top left here, you're seeing where the kernel is placed, and this is the original image. And on the right, you see the result on the final image. So what you're doing is you're taking the kernel at every position, and remember the kernel is 1/9 at each spot. And then you're multiplying everything and summing it together and replacing the center pixel by that value. Whoa. So the first row, nothing's happening because you're just taking the average of all zeros. Yes?
I think on the very latest IPython, this is broken somehow.
You mean Jupyter?
Yeah.
Yeah, sorry. Haven't tested it on that.
No.
Yep. So we'll have to update that. Thanks. Okay. So then when you get to the second row, now it's picked up one corner of it, and you can see that it's added, 1/9 to this value. And as you scan through it, it'll add, actually, this is an informative case here. So you can see that here it's taken 3 values, so this is actually 1/3 here. And as you scan through it, you get this mean filtered image of your original spot. Okay? So here's the output. Again, as I was saying, this is 1/3, 2/3. So it's the average of the footprint of the pixels in the neighborhood that the footprint covers. Okay, I'll skip this bit. So let's try this on real images. So here's your camera picture again. And let's just pretend we got a really crummy pixelated version of it. And so if we do the mean filter using the exact same tools, now it looks smoother. It's a bit blurrier, but it's certainly smoother. Okay, so min filter is the way to do smoothing on images. But it's actually one of the simplest filters. And so there's a whole bunch of other filters which are available in both Scikit image and SciPy.ndimage. And one of the most useful is the Gaussian filter. And what that's doing, again, it's averaging the pixels, but it places more weight depending on the distance of neighbors to your original one. So instead of averaging everything by the same weight as you do here, these pixels are actually further away from the center than these ones. So you should probably weigh them accordingly, if that makes sense. So the Gaussian filter is a way to do that. So from Scikit image, you can import filters, and that includes the Gaussian filter. That's not very obvious that it's different, I don't think. Oh yeah, okay, so this is kind of a rough sort of step function, and the Gaussian looks a lot more like a circle in a sense. And now for the image, I think I'd want to compare these two. Yeah, so you can see that this still looks quite a bit blocky compared to the Gaussian filtered version. Sorry, I'm rushing now. That's right. And so when you're taking bigger filters, in this case the size 20 filter, the Gaussian kernel removes a lot of artifacts that you would get from the mean kernel when there's banding in the image and so on. So you can see here, you get these vertical bands when your filter is crossing certain edges that are far away from your point of origin. But the Gaussian kernel, because it's downweighting those far away pixels, doesn't give you the same kind of artifacts. Yep.
In the physics, you can use circular security element for the mean.
It'll remove some of it, but you'll still see some artifacts. As long as there's edges, with high intensity drops in far away places, that's affecting your value locally. That's what's causing the banding. So you might not see it as blocky as this, but you'll see these angular ones. Okay, so this is an exercise, and I think it'll be the last exercise for the section because we're running a bit behind. So the idea is for you to create a kernel that will do a difference filter like we saw earlier, but it'll do it in a 2D image. And one should find differences in the horizontal direction, and the other one should find differences in the vertical direction. Yep, so do that, then I'll show you the solution, and we'll move on. The Sobel filter is sort of the standard way to do edge filtering, but it's better if you discover it for yourself. So as a couple of hints, you need these two kernels to be two-dimensional, not one-dimensional arrays. All right. Okay, so this is a teachable moment. Basically, this is your horizontal edge kernel. I've put a 0 in the middle just so that you're finding the gradient at each pixel instead of in between the pixels. That has some nice properties later on. And so you just do a row of -1, 0, 1, and then that tells you if there's a gradient between your left neighbor and your right neighbor. And vertically is just the transpose of that. Okay, so hopefully that makes sense.
Question.
Yes?
I got roughly the same effect with a very different one. That's just a 2 by 2 with ones and -1s and no zeros at all in there. Is that then not centered property? Or
Yeah, it won't be centered. It'll be a different shape to your input, which is not a priori a bad thing, depending on what you want to do. But when you're processing images in sort of a pipeline, these kind of shape changes can be annoying. So usually people, such as myself, prefer centered kernels. Okay, so can anyone guess as to why we're seeing this weird pattern? It's not super tricky.
noise?
No. So noise will give you patterns, but this is kind of extreme, right?
Because it's an integer image and you're pushing it to the closest integers.
That's right. So we're doing a difference in an integer image, and so anything that's 255 minus something else will loop around. So it's overflow. So this is why it's useful to know about data types as we talked before. So if we do image equals image as float of pixelated, hopefully that's going to fix things. There you go. Okay. So now you can see that there's kind of no gradient here. and then this is the vertical gradient, and this is the horizontal gradient. Okay, and there's more stuff here which you should do in your own time about the Sobel filters and using them to find gradients in images. But now I'll hand over to Emma.
Hi everyone, so welcome to the second part of this tutorial. During the first part, Juan showed you a few very important basic blocks of image processing, that is, images on numpy arrays, so how to manipulate pixels, what is the color or the gray value of a pixel, what is a filter for an image, that is how you change the value of a pixel from the neighborhood of a pixel. So now we will try to apply all that we have seen with Juan, and we will try to solve a whole, almost real-life example that you might encounter during your scientific work. It's actually an image from my lab, so I think it's a very important use case, but you might also have different use cases. And I think that for tutorials, we're also interested in knowing more about what you guys have as typical problems in image processing, what kind of images you process, what kind of operations you often do. And just for a quick survey, how many people here process images from time to time during their work? Just to, so say it's like 1/3 of the people. Yeah, so for the people who deal with images on a regular basis, I really hope that this tutorial will be interesting to you. And for those ones who don't work that much with images, knowing a few concepts of image processing might be useful, sometimes only to process 2D or 3D arrays that you might have during your work, even if it's not a regular image that you record with a camera and so on. So I hope it's useful for you as well. So this second part of the tutorial will focus on what's called image segmentation. So image segmentation is the labeling of objects of interest. So here, you have an image where you have a multi-phase material, and what I'm interested in is to label all the pixels belonging to each one of these blobs and to measure some properties that are important for the kind of science that I'm doing. So this could also be cells in biological images, for example, this kind of blob-like images. So that's why I think it's quite a frequent application. So what we do is that we start to open the image. So here I import the I/O module that Juan was talking about, the input-output module. And so in Scikit image, almost all functions are nested. They are found within submodules. So it's in a classical workflow with Scikit image, you will import a submodule from Scikit image, from Schimage, and then you will call a function in this submodule. So here it is, and then I plot my image. So I have all my blobs in the image, but I also have this annoying toolbar that comes from the microscope that recorded the image. So if I want to do robust image processing on this image, I first wish to get rid of this bar because it will do crazy things on the toolbar. So how can I do that? I can see that I just need to remove the last rows of the image. So I can either manually see the index of the rows that I want to remove, but I can also use some nice numpy machinery to do this, and that's what is done here in this a bit complex but one-line operation. So basically what I do is that I say the last line that I want to keep, it's the one where all my pixels are very dark. So this is this numpy operation. My image has gray values smaller than the threshold, and this numpy.all function. So this is really the power of numpy, that you have all these utility functions like np.all that you can use, and really the power of Scikit image, it's not only the functions that are within Scikit image, it's all that comes together with numpy, all that comes together with SciPy, as we saw with the different convolution operations. So also think in terms of numpy operations. So when I have determined the row, the last row that I want to keep, cropping my image to remove the toolbar is just a normal slicing operation that I can do here. So it's once again a very classical numpy syntax with a nice property that I don't have to specify the first row. And so now I can start playing with my image. A first inspection of the image is usually to take a look at the contrast of the image and at the distribution of gray values. Because here when I look at this image, I could think, okay, it's very easy with your own eye to distinguish the blobs from the background. But you can also see maybe or on your own screen that you have some noise on the image. And so how well are the two phases distinguished by their gray values? For this, the tool of choice is the histogram. And so the histogram function is once again found within a submodule of Scikit image, and this one is the exposure submodule because it will deal with the distribution of gray values. So let's import the exposure submodule, and then we call this dedicated function histogram, which will return the bins of gray values and the number of pixels within each bin. So I plot here the histogram. And so what you can see is that you indeed have two peaks. The darker ones, the darker one corresponds to the blobs, and the lighter one to the background. But there is still quite a strong overlap between the two peaks. So, for example, if we try to attribute the label of a pixel using only its gray value, what we'll do is we'll do a thresholding operation. That is, we'll say, okay, let's draw a line in the histogram separating gray values for the background and for the blobs. This is called thresholding, and you can do this either manually, saying, okay, this one it's at 130, something like that, or if you're smarter, you can use a dedicated function of Scikit image that is a thresholding function, and that will compute automatically the best threshold to separate the two phases. So the most common such thresholding filter, it's called O2 filter, and it computes the threshold that will separate the best the two phases. So let's first import the submodule filters, because threshold O2 is found in this module, and so it gives us the best thresholding value. But what's very nice is that it's something that's automatic. I don't have to inspect manually my image to know this best thresholding value. And for example, I could use this in a for loop, looping over a batch of images, for example, when the exposure changes, when my image gets lighter or darker. So what happens now when I try to threshold my image using this threshold? So as you can see here, it's not very good. So here I have plotted all the contour lines corresponding to the threshold value. So you can see anything, and it's normal because there are way too many contour lines. And here is the result of the segmentation. That is, white pixels are the objects that I'm trying to detect, and black pixels are the background. So you can still recognize the shape of the objects that I'm trying to segment, but it's really bad. It's very noisy. So it's not something that's satisfying, and we'll try to do a better job at segmenting the image. To do this, we'll use one of the building blocks that Juan introduced, that is filtering the image. Why do we want to do that? because when you take a look at the image, the reason why your eye is so good at distinguishing the blobs from the background is that your eye performs some kind of filtering. You use some information about the image, that is that pixels that are close together, spatially, should belong to the same face. So you kind of average together the values of the pixels that stand close together, and that is why your eye recognizes so well the different objects. So we will try to reproduce this for numpy arrays, and for this we will do filtering operations. So first, let me just zoom on a part of the image to show that. So here I zoomed on a little part of the image that is somewhere like, it's around here, I think. So we would expect this region to be uniform, at least in our material before the image was taken. As you can see here, and with the color bar, it's not uniform at all. So this random variations of gray levels that we do not link to a physical property of the material, it's what we can call noise. And the source of noise in the image can be manifold. First, it can be something in your material that you didn't expect, but more often it can come from the acquisition process. That is, you can have a low counting noise if your exposure time is not long enough. You have that on your cell phone where you're taking photos at night, for example. You have a lot of noise on the image, but it can also come from electronic noise on the sensor that will add spurious values. Yeah, question?
Is there any, because the size of your filter you now pick manually,
Mm-hmm.
is there any automatic or smart way to pick that, or is that just...
So that's an excellent question. Let me just come from, because you read faster than what I was explaining, but then I'll go back to your question. So in order to remove the noise, what we will do is try to average together pixels that are close to each other. Because if the noise doesn't have any spatial correlations, then random fluctuations will just cancel out. And that's really the principle of filtering. And so what we will do is use the median filter. I think you briefly mentioned it, but you just showed a Gaussian filter. And so what is a median filter? A median filter replaces the value of one central pixel, say this guy, with the median value of all pixels in a defined neighborhood. Why the median value and not the average value, for example, not the mean value? It's because it will allow to preserve better the edges, and it will be less sensitive to outlier values like very high or very low values. And a median filter will typically result in less blurring than a Gaussian filter. I think the median filter is the most useful thing in image processing that people usually don't know, because everyone knows about Gaussian filtering because you have that in Photoshop. People use it a lot to have better looking images. But if you want to have an accurate, if you want to preserve features and edges, then a median filter will do a much better job. So, as you asked the question, you have to select the size of the window in which to compute the median value. So how should you do that? Obviously, the more pixels you choose in the window, the more denoising you will have, because random noise will be more cancelled. But you will also be more prone to removing small features. And especially, I think you also said that if you have curvatures, then the median filter will remove it. And so the the typical rule of thumb would be to select a window size that is of the order of the radius of curvature of features that you want to keep. So usually, if you have, for example, here, the blobs are very large. They have curvatures are not high. But if I had like finger-like structures with tips with very high curvatures that were important for my application, then I would be very careful about choosing a small size of median filtering. For example, I don't know, 3 by 3 or 5 by 5. And if you want a more robust way of choosing the size of the window, it should scale really with the radius of curvature of objects that you should keep. So one way of doing this is to iterate. That is, you perform a first denoising, then segmentation. Then you measure the curvatures of objects that you get. And then you go back and say, maybe this was not good. Let me try it again. Does that answer your question? No? OK, so let's take a look at the result of the median filter. So that was noise. So I think I already imported this, but so here is a call to this median filter. And as you can see here, the result looks much smoother, but still it doesn't look as if we have blurred the image as we could have with a Gaussian filter. I hope you agree that this is a pretty good denoising. And if we want to check this, we can take a look again at the small region here that was supposed to be uniform. First, you can see that the range of fluctuations is much smaller than what we had before, and also that fluctuations typically vary in a smoother way. That is, now they are more spatially correlated, and you don't have short-range noise as we had before. So let's take a look at the histogram of the new image, that is the median filter. So you can see that instead of having this big potato-like histogram that we had before, that's what we say in French, potato-like histogram, but I don't know the English for that. And now the two peaks are much better separated. Of course, we still have some overlap, but it will be now much easier to do a thresholding. And that's what we do here, using, again, this threshold O2 function to determine automatically the threshold. So yeah, I think I just zoomed on the small part of the image. So what can we see? We can see that the contour of the blobs is well delineated. We still have a few pixels that we might not be that happy with. And this will be the subject of the rest of the talk, how to clean the image. Just want to mention, I've put a few links in the tutorial if you want to go further and see more complicated cases, because I have to say that for this tutorial, I wanted to show a full example from a real-life application, but I also chose something that was quite simple compared to what you can encounter in real life. So if you want to do more complicated things, I've put a few links with examples. For example, here a link to thresholding, where you have uneven illumination within the image, and you might want to select a different threshold in different parts of the image. So this is covered by this example of the example gallery of Scikit image. By the way, let me take a few seconds to advertise the gallery of examples. How many people here are using Scikit image? Just to, and are you using the gallery of examples from time to time, or did you know about this? It's actually a very nice way to learn about image processing, because you have this whole gallery of examples that was originally adapted from the one of Scikit-learn, which is also very nice. And you have this graphical example with a short title. And if you have an example, well, a problem in mind, and you don't really know how to solve it, you can just go to the gallery and see if something looks like what you would like to do. And you can actually learn a lot about image processing and the different algorithms that are available. You can actually learn a lot about applied mathematics, just starting from this gallery of examples, because image processing is applied mathematics plus some knowledge of how to combine the different algorithms together. So let's go back to our image processing problem. So now I'm quite satisfied with my thresholding. So I can use numpy Boolean operations to define what's called a mask with numpy vocabulary. That is, take all pixels that are smaller than the threshold defined by Otsu, and this gives me this binary image. So it's composed only of true and false values. So as an exercise before we move on, I propose that you try a different kind of filter, because here we saw the median filter, but other very nice and powerful filters are also available in Scikit-image. For example, the bilateral filter that is quite close to the median filter, but it uses one supplementary ingredient. That is, it will average one pixel with its neighbors, but only if they are close enough in terms of gray values. So it will not average a pixel with values that are too far, and that can be interested in some applications. So please take a few minutes to do this. I'm just telling you that the bilateral filter is found in the restoration submodule. So do some Scikit-image import restoration. Interactive work. Okay, and use the introspection that IPython proposes. That is, when I just start typing restoration dot and then tab, I have all the different functions that I have in this restoration submodule. So even if you don't really know what you should do, you can just select one and then ask for the doc. Oops. Restoration. And then you will have the documentation. So. Oh, I think it's because you didn't launch the IPython notebook from the root of the directory. Can you launch it from not lectures but one level above? And then it should be okay. CD, yeah. Then do it again.
Then I should launch it from there.
It should be okay.
Okay. So does it need to be there in order to load all images properly? Is that a specific reason why?
Oh, it's the way the IPython notebook handles paths and.
Because they're like relative paths, they're
Yeah.
not like absolute. Okay. It's not loading again. Yeah, sure.
But it's not.
Or maybe I don't understand why there are two now.
You don't have the good version of the tutorial. How did you download them?
I cloned the master branch.
Oh, but it was not the master branch. It was the EuroSciPy, the zip file, the zip link that. Yeah, if you cloned, it's.
I mean, there was no specific link to download. I saw the Git
Yeah.
repository, so I downloaded it. So
Sorry
there is the
about that.
lecture
Yeah,
series.
but it's not the.
Okay, so what
It
is
was
the
a EuroSciPy branch.
EuroSciPy? Okay,
Yeah.
so there is a EuroSciPy here.
Yeah, but it's last year's.
There is a 2015 as well.
EuroSciPy. No.
Yeah, 2015.
Yeah, but it's SciPy, not your SciPy. Sorry about that. EuroSciPy 2015. All attached. Okay. Okay. So, let's try another filter. Phase separation, and then I have to specify a window size. So let's try to use a larger one. Okay. So, yeah.
If someone has manually labeled images, or the areas of images that are manually selected, are there utilities to set up a pipeline so that you write a loss function so that you see how well you reconstruct the manually selected images, and to write a pipeline kind of like scikit-learn pipeline?
So the pipeline way of using Scikit image is that you have this simple API where you call functions on images and with some keyword arguments, and usually what you get out of these functions are images. So of course you can use this in a pipeline workflow by doing one operation after the other. There is no specific framework, especially for the visualization part, that is included within Scikit image. We have some examples in an experimental viewer, but it's not maintained a lot. And
I would say depending on what you're doing, you would want to just plug in the scikit-learn pipeline. That's the power of SciPy, is that we're all using the same data structures, so you could conceivably do what you want.
Scikit-learn just got worse than new transformer that takes a function and makes it a scikit-learn.
Yeah, exactly.
Okay, but let's talk about this later. Okay, so what is nice is I have these different keyword arguments that I can use. So it's first possible to use the function with just default parameters and then to try to fine-tune the results by changing the keyword arguments to values that are not the default values. So it's a very progressive way of learning image processing, first using the default values and then trying something else. And here I can see that, for example, if I'm very strict on the sigma range, that is, I want only pixels that are very close, then I think that I won't do any denoising. Is that true? Yeah, I have much less denoising than when I had this. Oops. You see? So the bilateral filter gives you more possibilities to tune the result of the filter. Okay, I have added a paragraph to the tutorial just to mention that it's also possible to do segmentation operations that are more advanced than just a simple thresholding once you have filtered the image. Typical segmentation algorithm will also use spatial information about pixels. That is, they will try to put in the same phase with the same label pixels that are close together. And we have a few examples of such segmentation algorithms within Scikit image, such as the watershed algorithm. You have a link, or the random walker algorithm. So there is once again an example that you can run and see that the result is actually better than what we have here with just the thresholding. So when you use more information about your image, usually you have a better result. The drawback is that you can input some information on your image that is actually not completely true, and then this can result in more artifacts than if you had used simple operations. So it's always a trade-off. So let's move to image cleaning now, because we have done this segmentation. We have a binary image, but you can see here that we still have these small regions that are spurious regions. We don't want them, and we also have some holes here that we would like to fill. And the good thing is now we have a binary image of Boolean values, so we can apply operations that are specific to this kind of images. One of them is the whole field of the so-called mathematical morphology that does operations not only but also on binary images. And so we will import this submodule. And one function that's very useful within the morphology submodule is this remove small objects. So this function does exactly what we would like to do, that is removing the small objects. And we have a minimal size to give to the function. So here it's quite arbitrary, but I give 300. And so let's look at the result. So we've removed all the small regions, and now we would like to fill the small holes. So filling small holes is exactly the same thing as removing small objects in the logical knot of the image, so operations on Boolean images. So we do this by calling again remove small objects, but inverting true and false, black and white in the image. And then, of course, we need to go back to the initial black and white. So that's what we do here. And then we're done. So we have a good segmentation, at least we're satisfied with it. And now what we want to do is to measure the properties of all my different objects. So the first thing to do when you want to measure properties of objects is to assign a different label to each of the objects. Because here, the different blobs, they all have the value 1. I want then to have a different index for each blob. So once again, there's a dedicated function for that. It's not there's an app for that, but there's a function for that in Scikit image. And it's actually a good way to think. If you want to do something in image processing and it looks simple enough, there might be a function for that. Don't try to re-implement the wheel and first take a look at the example gallery, Google about it, and don't write functions with 200 lines of code where you do things that already exist. So this function is called found in the submodule measure, and as you can see here, we managed to have a different index for each one of the blobs. And the following step is to call a function whose name is clear enough. I think it's region props. It computes the properties of the different labeled regions in an image of integers that is an image of labels. So we have such an image here. It's the output of my label function. And so I compute props. So props is actually a complicated beast, but it's a list of properties, and each properties has an object-like syntax, where, as you can see here, I can compute all the areas of my blobs by looping over the property objects. And it's the same with perimeters. The names are quite obvious, but you find all of them in the documentation. And for example, I can plot here the circularity ratio, that is the ratio between the square of the perimeter over the area. And when this ratio is very close to small values, I don't remember the exact value, but then it corresponds to round objects. And when the ratio is large, it corresponds to objects that have more complicated shapes. And for example, computing such properties can be used to do after classification of the different objects. You can switch then to scikit-learn and do some classification. So it's a nice way to use the different packages of the ecosystem together. So I have 5 minutes left, and I would like to spend this time, well, first answering to your questions, but also showing you how you can switch to the processing of one single image, as we did here, to the processing of whole collections of images. Because usually, when you're in the industry, when you're in academia, you have a large number of images, at least when you're using Python. You have very fast CCD sensors, you have experiments that you want to follow in situ, and with this you will often be flooded under gigabytes or even terabytes when you have 3D images that you have to process. By the way, Scikit image is quite compatible with 3D images. We didn't show you examples with that, but both Juan and myself are mostly working a lot with 3D images. So it's a nice feature of Scikit image compared to other image processing packages, that you can apply exactly the same functions with the same API on 2D and 3D images that could come from MRI, X-ray tomography, or so on. So what will you do when you have a whole collection of images instead of one? Typically, you need to do things that are more robust, because when you have one image, you can tinker with parameters, you can do a lot of operations one after the other, and once you have the solution, you're happy. But there's no guarantee that this will work when you go to another image. I'm sure that this has already happened to a lot of you. So one first thing is to try to determine the parameters of the image processing functions in a semi-automatic way. That is, to link them with properties of the images, like the typical size of objects, the typical noise of the image. Also, in terms of code engineering, it's a good practice to to divide the different operations into functions, because if you have a for loop on images with a lot of operations, then your code will be very ugly and very difficult to debug. And also, when you have the same operations to apply on a batch of images, then it's a perfect application of embarrassingly parallel computing, because usually you can process the different images together, and this really calls for using the different possibilities of multiprocessing computing that you have in Python. And here I mentioned the very nice joblib module. I think Gail will give a lightning talk on it at the end of the conference. That provide helper functions to do very simple parallel computing where you have embarrassingly parallel for loops. So let's take a look at how we can do that. First, let's define a function to remove the information bar. And as the location of the information bar might vary from one image to the other, we don't have a hard-coded value. We put something that determines the value of the row index in a more automatic way. Then, in order to clean the image, there's always a problem of what should be the size of the small objects that you remove. Because if you have very large objects in your image, then it will be okay. You can remove a lot of the noise-like objects. But when you start having small objects, then it's not obvious whether you should remove small objects or not. When you have small real objects. So here, what I do is that, so I don't have a lot of time to go through this, but I defined the size of the objects to remove from typical sizes of objects determined by a first segmentation. So this is much more robust, once again, than the hard-coded value. So let's do this. And then I have a main-like function to process an image. In order to retrieve a list of image files, the glob module is very useful. I don't know if you use it, but you can use wildcard-like patterns. It's very nice. And then, oops, I process all images in a for loop. And here is the result. So even if you have automated everything, that you don't have any manual operations to do, it's always a good idea to take a look at the final result to be sure that your image processing pipeline didn't do any crazy things. So this is the end of this tutorial. I really wanted to insist on the fact that it's important to be able to process not only one image, but going to one image to a large collection of images is important as well. And do you have any questions? If no, it means, oh yeah.
After you finish all this modulation, are you normally putting everything to a kind of algorithm or pipeline so that it can be run different platforms?
So usually, I'm not sure I understood your question. Is it?
So basically, are you guys using HPC? Because, well, given the size of the images you're processing, normally cannot be handled by a computer to handle gigabytes or terabytes of data.
I'm using Scikit image on images that are several gigabytes, but we try to use very standard tools, that is relying on numpy arrays, and we don't use other tools like, I don't know, GPU computing or...
Parallel computing is basically...
So parallel computing, so first there is a possibility to process different images on different cores, but we also have some experimental framework to do this. by dividing an image in windows. Another possibility that we are testing is to use task arrays. Don't know if you use this tool. It's actually a complicated trade-off to have a good performance for large size images or large number of images, and to be standard enough so that it will remain very easy to use Scikit image, and so that it will be compatible with all platforms, because it's really compared to other imaging processing modules, Scikit image is really well adapted to people who start using image processing, who are not expert coders, who want to do C++ or so on. So we have to remain simple enough so that this kind of people can continue using it. But at the same time, of course, we have to be as competitive as possible in terms of execution performance. So at the moment, there are discussions, and we're trying things especially in terms of parallel computing, but I don't think we have a stabilized solution yet.
Well, I think the shorter answer is most of the time you would chunk your images, right?
Yeah.
So you just look at different chunks of different cores in your HPC. So that's what I've done in the past. There's a whole bunch of packages that are coming out that are trying to do this more transparently, and they're not on Scikit image, but they will probably use Scikit image operations, but they will just automate the chunking for you. So task arrays follows in that category.
Yeah, chunking is also what I do. Yeah.
X-ray, you might want to look at, and what was the YT, which I've never used, but they have very impressive demos of doing things on enormous volumes.
Other questions? So if you have other questions and you don't want to ask them now, we will be...
switch to the index, just to show... so we'll be having a sprint on Sunday. Please come to that. We're very friendly to new contributors. And 3 years ago, I was a new contributor, and now core dev. So come to that. And also, you can always find us on Gitter, which is this GitHub integrated chat system. So feel free to always find Emmanuelle and me during the conference if you have questions. And also you can always find us on Gitter. We have a mailing list, GitHub. And finally, we have a paper. If you use Scikit image in your research, please cite.
Please cite the paper. Okay, thank you very much.